to be pondering some questions of like, why can a small spark, or how can a small spark create such a huge explosion? Like creating fireworks, because they come in little tiny packages. Or like, how does something small like TNT create a huge explosion? How do things move around us? How do I move? How do objects move? Well, the reason for that is energy. So today we're going to be learning all about energy. Energy. So what is energy? Well, the scientific definition of energy is the ability to do work. Now, work doesn't mean like you're going off to work or you're working out. Work in science is the transfer of energy. So that means energy is just describing how things change and move. It's describing things that are currently changing or moving, or it's describing the potential of something to change or move. And we can calculate this, just like how you can calculate someone's mass in kilograms, how you can calculate how long or the height of something in meters or inches or feet. You can also calculate how fast things are going, miles per hour, meters per second. And so energy can be measured, and its measurement is called joules. You might be more familiar with a different measurement of energy called calories. Calories is how we measure the energy in food, like Oreos. Calories are just a measurement of how much energy is in your food. So that means food, like Oreos, have energy, even if it's not moving or even if it doesn't seem to be alive. That means energy then is potentially all around us. It's in you, it's in me, and it's in everything in this room and everything in your room. Energy is everywhere, even in this little diagram here. Hello, little penguin. So here's a little penguin on a diving board. He's not moving, just standing there. Does he have energy? If he's just standing there, does he have energy? Yes, yes he does. And there's a lot of different types of energy that we could describe that's occurring here. He's standing, he's a penguin, so he's probably breathing. So he's got all of these energies that's related to biological processes. So one type of energy that may not be so obvious is called potential energy. He has potential energy standing there. So what is potential energy? Potential energy is stored energy. It's energy that's based on position, like height. So like how the penguin is up high on a diving board. So because of his height above the earth, he has potential energy. And then what would happen if he jumped or if he fell off the diving board? He's gonna fall, like when you fall down. And why or how or what makes us fall? Gravity. Gravity is what brings us down to earth. So that means that this particular potential energy that we're talking about, when it's based on height like this, is called gravitational potential energy. It's describing the energy stored in an object due to its position above the Earth's surface. So this type of potential energy is affected by gravity. So let's take a look at this gravitational potential energy. Here is our little penguin on a diving board, and there we've got our T-Rex on a diving board. They're both at the same height. Who do you think has the most potential energy and why? In other words, who has the most potential to make the biggest splash when they fall? It's the T-Rex. Let's watch. So the T-Rex has made the biggest splash because he had the most potential energy. Why the T-Rex? Why did he create the biggest splash? Why did he have the most potential energy? Has to do with mass. Mass is a measure of the amount of matter in an object. That's what mass is. It's like a measurement of how much stuff is in something. So potential energy depends on mass. So the more mass, the more potential energy something has. So if you're going to have a cannonball contest with someone bigger than you, you might not win. You might want to like grab some weights or something to give you some more mass to give you some more potential energy. So what else does potential energy depend on? So let's take an example here at my desk. So I have two books. Let me move some things out of the way. These books have like pretty much the same amount of mass. They're the same size. So now I have one lower to my table and one higher to my table. Which one has more potential energy? In other words, which one will create more force when it hits the table? The lower one or the higher one? There's the lower one. The higher one. The higher one makes a bigger sound. So gravitational potential energy depends on height. When it's lower to the ground, it doesn't have as much potential energy, which means it's not going to make much of an impact. But the higher something is, the more gravitational potential energy it has and makes more sound. So gravitational potential energy, that is stored energy. It's based on position above the earth, and it depends on mass, and it depends on height. The more mass something has, the more potential energy it has. The more height something has, the more potential energy it's going to have. And there's many different types of potential energy besides gravitational, which is what we've been looking at. There's also chemical potential energy that's stored in food. This gives you energy. It can also be stored in, grab one, in batteries. Batteries are chemical potential energy because they have the potential to give energy to something else. There's also elastic potential energy where things can be stretched or compressed. And there's nuclear potential energy, which is stored in chemical bonds. But what do all of these have in common? What do all of these types of energies have in common? Well, for one, they're not really moving. They don't deal with movement. And you might be wondering, isn't energy about movement? Well, yes, part of it is, or a lot of it is. That's kinetic energy. And kinetic energy is all about movement. So energy an object has due to its motion is kinetic energy. And you can also measure how much moving or kinetic energy something has in joules. And just like potential energy has different types, so does kinetic energy. You can have radiant or electromagnetic kinetic energy, that's light. Obviously this isn't light right now, but light is a kinetic energy because it has to move in order for you to see. There's thermal, like if you rub your hands close together like this, if you try this right now, you're gonna feel heat coming in your hands. And you can see that my hands got a little red from all of that heat. This is thermal energy because it's moving. It has to deal with movement. Electrical kinetic energy because charges move. That's electricity. It has to move from one place to another. Sound, which is like what I'm giving you right now, is sound. And sound is kinetic because it has to travel from my mouth into your earballs. It's got to travel. Sound is kinetic energy. And last, the most common and the most obvious is mechanical kinetic energy. That's moving. So jumping, running, a ball rolling down a hill, biking, your car moving. That's all mechanical energy. Or like when our penguin jumps off the diving board. That is kinetic energy. So if potential energy depends on mass and height, what does kinetic energy depend on? Let's go back to our diving board example. So let's look at the penguin and the T-Rex, and let's watch them jump. And let's think, who has the biggest splash and why? So the T-Rex has the biggest splash. Why does he have the biggest splash? Because he has more mass. Just like potential energy, kinetic energy also depends on mass. Because the more mass something has, the more amount something has, the more energy it can create. And so the more mass, the more kinetic energy, the more force that can be exerted. So for example, let's say that a house is on fire and you've got two firemen. You've got a tiny fireman and a really heavy buff fireman. Who's going to be able to break down the door? The heavy fireman. He's got more mass and he's able to break it down. The kinetic energy doesn't depend on height though, like potential energy. I have energy right now, but I'm on the ground. So kinetic energy, it's all about moving, and it has to depend on mass, but what else does it depend on? So let's think for a second. If I'm walking or kind of just swaying like this back and forth, do I have a lot or a little kinetic energy compared to, what if I run or jog in place? Do I have a lot of kinetic energy now? So which one has more kinetic energy? Walking or running or jogging? And why? Well, jogging and running, obviously you have more kinetic energy. I mean, you can feel it if you're running, if you're out of breath, but it has to do with speed or velocity, how fast something is going. Let's think again to our firefighters. So he's got to break down a door. Do you think he's going to break it down if he just kind of walks up to it and tries to push on it? Or is he going to break it down if he runs at it really fast? He's going to break it down if he runs at it really fast. Why? Because he's moving faster. The faster you go, the more energy you can have. That's why, like for example, if you're talking about like a bullet, that's why a bullet can be so deadly. Even though it's itty bitty tiny small, it can get up to speeds of like 1,800 miles per hour. It can have as much force as a Honda Civic going 10 miles an hour. Because it's going so fast, it has so much energy. So kinetic energy depends on mass, how much there is of something, and speed. More mass, more kinetic energy. More speed, more kinetic energy. But now as we finish up, where do we get our energy from? How do I get my energy? When you wake up in the morning and you feel groggy, or maybe your parents feel groggy, what do they reach for? Maybe coffee, maybe food. So where are we getting our energy from? Food. Hopefully more nutritious than Oreos, but we get our energy from food. And if we remember, what kind of energy is food? Potential or kinetic? It's potential energy. It's chemical potential energy. That means that kinetic energy gets its moving energy from potential energy. It's this circle. So like when we look at the penguin jumping off the diving board, he starts with a lot of potential, and then as he falls down, he's losing potential energy as he's gaining speed, because as he falls, he's going faster and faster and faster. And then when he makes his big splash, he has now no more potential energy, but right at that moment where he splashes, he has a lot of kinetic energy. And then if he wants to go again, he just has to climb back up and go back down. And so it's this cycle. So for example, here. So we have a picture here of divers. So at the very top, you have the most amount of potential energy in this scenario because you're at the highest point. And then as the diver jumps, that potential energy transfers into kinetic. So the kinetic energy is getting energy from gravity, which is related to that gravitational potential energy, and it helps them fall down. And he goes faster and faster until he hits the water. And then at the water, it has zero potential energy in this scenario. And then if he wants to go again, you have to go back up the stairs to the top. So as you go back up, you're gaining potential to go back. This whole cycle. So let's look at this again and think of it in kind of a broader tense, a broader kind of idea. Because right now we're just looking at the most common energy transfer from potential to kinetic. So let's watch the penguin dive. He starts with potential and he goes down. What other energy transfers can you think of happening? How does a penguin create a splash? How do we get sound? Are those energies too? So those are all types of energy conversions. It's this process of changing energy from one form to another. That's energy conversion. They happen all the time, every time. And then this relates to the law of conservation of energy. If you notice in our penguin example, and in this example, it's a circle, like the circle of life. There's no ending, there's no beginning. That means energy always is transferring. That means that it's never created out of nothing and it's never destroyed. That is the law of conservation of energy. It's a description of this phenomenon. It means that energy is never destroyed, it's never created. It's always a cycle. So the total amount of energy never changes. It remains unchanged. That means all of the energy on our planet is all of the energy it's going to have. So even though many energy conversions may occur, it's just transferring from one to another. It's not coming from nowhere, just like our diving penguin. It could also be with Newton's cradle. So when I lift one up, it goes down. So I lift it up high. The pendulum or the marble has a lot of potential energy. And then when I drop it down, it gains speed. So here it would be going the fastest. So it would have the most kinetic energy. And then it transfers it through the marbles and transfers the energy to the last one. So this is a perfect example of the law of conservation of energy, where energy is transferring from one to the other. And it eventually stops here on Earth because the air is slowing it down. All right, that is it for today and our little bit on energy. Until next time, see you later.